Hello everyone and welcome back to AP Biology with Mr. Jennings. Today we're going to talk about carbon. So we talked about chemistry basics, we talked about water, now we're going to talk about something more important than anything else, carbon. Now why do we talk about carbon so much in biology? Well, it's neat. Carbon is actually one of the very few essential elements that we talk about, and we talk about consistently. Carbon has its own dedicated field of chemistry known as organic chemistry. And what makes carbon so special is that it can bond 4 times. See, if you remember from your basic chemistry, and if you haven't had chemistry, that's fine. Carbon has what we call 4 valence electrons. That means these are the 4 outermost electrons. And more often than not in chemistry, the outermost electrons, these valence electrons, is where all the action happens. And a good general rule of thumb is you can have 8 valence electrons. Now the reality is when you get into orbitals, it's much more complicated. But for simplicity, we usually see we have 4 valence electrons. That means you can take 4 more electrons. That means you can bond potentially 4 times. So you get 4 potential bonds. Because it can bond 4 times, it allows for what we call an infinite of possibilities. What that means is carbon is one of the few elements that can not only bond to, say, hydrogen, it can also bond to other carbons. And those carbons can bond to, say, like hydroxide, an amino group. Hold on, make this an amine group here. Ignore that H. Alright. More hydrogen. It could bond to carbon, which can bond to other carbon, which can bond to carbon. It allows for an infinite loop of carbon chains. And this is a very important field of chemistry, especially regarding plastics. Now in biology this matters because, well, carbon's the key organic molecule. Organic atom. It's the thing that forms the basis for every organic molecule, which we'll talk about later. Now, carbon has some unique chemistry about it. Not only does it bond 4 times, but because it's infinite bonding, it has different arrangements, and that's isomers. Isomers are molecules with the same molecular formula, but different structure. The general rule is anything more complex than propane. Now, if you don't know about propane, propane is a 3-carbon molecule, all single bonded. Anything more complex than this has at least 1 isomer. What does that mean is, say we take butane here, which is 4. It can look like this, or it could be this. And it gets infinitely more complex from that. So, since everything has at least 1 isomer associated with it, that matters a great deal. And we'll talk about that in a moment. But first, let's talk about the different types of isomers. So, we have structural isomers, which are same formula, just different arrangement of atoms. And that's what I talked about here with butane. So we have butane, and it's in linear form, and we have isobutane, which is a branched butane. Chemically speaking, they're the same. At least chemically, formatically speaking, they look the same. But when you draw them out, this matters a great deal because, as we're going to find out, the structure dictates the function of most molecules. Now, another type of isomer is a cis or trans isomer, which is different positions around the double bond. So, let's say here we got the double bond right here. This is our double bond. And look at these, what we call functional groups. These are where these things right here, the CH3s, they're just carbons. But these things are a little different. So look, on a cis molecule, they are on the same side of the double bond. So let's say this was an imaginary plane. If they're on the same side, like we see here, this is what we call cis. They mean on the same side. Trans means they are transverse from each other. One's on this side, and the other is on the opposite side. So we call that a trans molecule. In this case, we have butene, which is the code for a double bonded butane. And it is cis-2 and trans-2. The two, when we talk about IPAC, nomenclature just tells you what carbon it's branching off of. That's kind of beyond the scope of this course, but you may see this notation quite a bit. And lastly, there is enantiomers. Excuse me. These are mirror images of the central atom. So these again are the same chemical formula, just different because one's what we call left-handed. This is my left hand, looks like a right hand on the camera, and right-handed. And as you see there in the picture, they look similar, but that placement of what we consider this functional group, this thing right here, matters a great deal. And like I said, structure dictates function. Now, these functional groups I keep mentioning here, they can modify the properties of organic molecules. The addition of just one of them, say like hydroxide, can change the entire chemistry of a compound. There's more of them than I'm willing to get into in this video, but you need to be aware of them. So what does really all this matters is that, let's go ahead and switch over here. What really matters with all this is that certain compounds, their structure really matters when we talk about certain things like enzymes. The shape of an enzyme is really important. This active site, the area of the enzyme that the reaction actually takes place in. If the compound is slightly different, it won't fit as well into that enzyme. And because it doesn't fit well in that enzyme is less effective. And that's why functional groups, that's why types of isomers matter. So enantiomers, those, like one example is dopamine. There's left-handed dopamine and delta dopamine. And those dopamines, one reacts perfectly fine in our brain. The other does not. It doesn't actually do any effect whatsoever. The proper effect, at least. And because of that, it's not as effective. And your body naturally produces a ton of different isomers because there's infinite combinations. There's no strict rule saying it has to bond this exact way. And these different little isomers will have an effect in the chemistry. Now, in chemical world, these isomers matter a lot because of production. In biology, they matter because of our function. If you change the isomer, you may change the overall function of things. And we're going to talk about some different isomers when we talk more about the different classes of organic molecules. That's all I have for today on this video. Keep in touch and keep watching. There will be more on this later. Thank you.